Okay, refraction. We talked about reflection. And the thing about reflection, do waves reflect? Yes. Does matter reflect?
No.
Well, in other words, if I have a ball and I throw it down at a 10-degree angle, it's going to come up at a 10-degree angle. Yeah, so even matter follows that. But only waves refract. And when we refract, we're talking about basically transparent material for that wave. Now remember, we already learned that different kinds of waves, things are transparent to different kinds of waves. Obviously, like earthquake waves travel through like rock, things like that, ocean waves, stuff like that. When we think about light, we think about transparent, like visible light on that. But refraction is the bending of a wave, its change of direction due to a change in the wave speed in the medium. This is where that idea of that light slows down comes from. Now keep that in mind. That does light ever slow down? No, but when it like goes through the windows, it takes time for it to get through that transmission speed. But we still call it the speed of light in the window and all that stuff. Now a good way to look at this was actually, we do have a mechanical way to see this. Now, any of you have ever used a push mower, manual push mower, you know the blade basically goes like this. Well, before they had gas mowers that had the little blades that go down the bottom, things like that, they basically took that push mower and they put a motor on it. Make the blade go around. They're very heavy and very hard to push. So usually they're motorized. In other words, you push a lever and it goes by itself. So if we took our motorized thing here and it went off the sidewalk and this wheel goes in the grass, what's going to happen to the speed of that wheel? It's going to slow down. Is this side going to slow down? No. So this whole thing is going to pivot around. It's going to curve until it goes off on that straight line. So it's traveling that straight line. It's going to curve until it goes into that straight line like that. Basically, that one slows down. It's going to pivot. Works the same way the other way. If we are going out this way, this wheel would have gotten to the concrete first, and it would have sped up and caused the whole thing to rotate that way. So we have a change in speed. Even marching, when we marched parade drill, which was like 9 ranks across, whenever we stepped from the concrete onto the parade field, which was grass, we'd slow down. Just going from, because it's much easier to walk on the concrete. As soon as we got onto the parade field, everybody actually kind of bunched up because you slow down a little bit. You have to be very careful that you maintain those ranks and things like that because you did slow down. Anybody need more time? Now notice the change in wavelength. This change in speed is because of a change in wavelength. It's the wavelength that changes our speed. Keep in mind, any wave, velocity equals lambda f. Now back when we were talking about Doppler effect, remember we said the velocity doesn't change. But with refraction, velocity does change, and it's the wavelength. Wavelength goes up, velocity goes up. Wavelength goes down, velocity goes down. But frequency remains constant. Frequency never changes. All right, the frequency does not change. It's the wavelength and speed that change. These are water waves. As the water goes into a shallower area, so here is our boundary. Probably in the wave tank, they put like a piece of glass. They put a triangular piece of glass here, made it a little shallower. The wave went this way, then it changed and went off in that direction. This happens at the beach. If you're ever at the beach, watch the waves coming in. Mostly, especially if you're in a cove beach, but most of the waves, do they come at an angle or parallel to the beach, or at least close to parallel to the beach? Parallel. You'll notice the waves pretty much come close to parallel. Some beaches are a little different, like it's a very open beach, things like that. Like North Beach at Point Reyes, they come in at an angle, they don't really have a chance because it's a very steep beach. But most beaches, as you get shallower, the waves will tend to go and try to be parallel. So they're always going to be more parallel to the beach than they were farther out, because that's just the way beaches work. Because the water gets shallow, they'll turn in until they're parallel. Go up someplace like La Jolla, that's very long, it's a very shallow, it's very, you can, in La Jolla in San Diego, it's like, I think, you can be like 200 yards off the beach and you're like only in waist deep water on that. And the waves are all just parallel. They come in parallel like that. Of course, you get out, you get about 300, 400 yards, it kind of drops off. So it goes from like about 50 feet to like 3,000 or something like that very quickly. But it's very shallow, then drops off on that, so they tend to be like that. Anyone need more time? So light bends. Now light bends towards the normal when we go from higher to lower. Okay, so here's our normal. So light is going to bend. So we have a high speed to a lower speed on that. And so if our wave comes in, here would be our incident, what we would call the incident ray, the refracted ray, like that. So if we're going from this side, we're going to bend toward the normal. We bend toward the normal. If we're going out, we're going from the lower to the higher speed, we're going to bend away from the normal. Away from the normal, like that. Remember, this is for any type of wave, not just light, but earthquake waves, things like that. In fact, I've read some theories about the Bay Bridge during the Loma Prieta quake because of bending of earthquake waves in underground. The Loma Prieta earthquake was about a 7. We'll just round it off. It's about a 7 earthquake. But because waves refracted underground, they think a couple of waves had some constructive interference right underneath the Bay Bridge, and it actually experienced the equivalent of an 8 earthquake. Because these waves got there, they made the wave bigger, and that's why the Bay Bridge, the part collapsed on that. Anyone need more time? Works for sound. Refraction of sound. Sound bends toward the cooler medium. It's going to bend toward the cooler medium on that, whether it's air, water, etc. So it bends toward because it's slower up here than it's down here. So this part's moving faster, that part, so it bends up. Remember, warm air, speed of sound is faster than cold air. It's kind of like that. Think about our little mower there, right? It's going to bend that way. Cool air, warm air on top, cool air on the bottom, goes down like that. So you hear different things on that. So that's what happens with sound. Questions? That's why in the evenings, like you're in a warm evening and things like that, you might hear, if you're on a lake, because you have the cold lake water, warmer air above, you're somewhere, and it'll bend the sound so you can hear the sound on the other side of the lake on that. Whereas you might not hear it as much during the day because it warms up the ground. Air would be a little cooler than the ground below, that sort of thing. Oh, sorry. Everybody get this one? One more time. Now light. Light passes from one medium to another. It appears to change speed. There that word appears. Appears to change speed because light. Light ever change speed? No. Remember, light only travels at one and only one speed. 3 times 10 to the 8th meters per second. Light rays change direction. So notice here we have this light ray going from air into the water. Water moves slower. It moves in on that. Now remember, light does not change speed. It's that transmission speed. This is what we're talking about. Why did they call it the speed of light? Because they didn't understand the nature. It's kind of like, there's a lot of things like that. Because these rules were made like in the late early 1800s. This is when they're making the rules and they thought, well, it looks like it slows down. Light slows down. Okay, they accepted that. It wasn't until later on they discovered the transmission. Same way with electric circuits. Is why we even still draw electric circuits always from the positive end of a battery to the negative end, even though current actually comes out of the negative end of the battery and goes to the positive. It's the opposite direction. We still draw it from positive to negative. It's because the rules were made long before they understood the nature of the thing. Anyone need more time?
Yeah.
So if we looked at this, now if I didn't have any, say I didn't have any water in this tank. I didn't have any water in the tank. basically what would happen is my ray would go down like this, and it go out at the same, at an angle like that. That would be if there was no water in the tank, right? It hit the bottom, it's going to go out. But since I have water, when it hits the water surface, it bends inward. So notice it strikes the mirror at a point to the left of where you would. So it's moved it a little bit, comes back up, that angle of reflection moves out. But notice these two rays. Those two rays are what? Parallel. So it came out still parallel, still going in the same direction as it was. Whether there's water or not, it's going to come out going in the same direction. But now it's been moved over a little bit, the refraction, because basically this angle, if we looked at these two angles, the angle of reflection here at the bottom, when you add the water, has been made smaller because of the refraction on that. So if you're over here, you would see that, you would have saw that ray with no water, but you wouldn't see this one. But if you saw this one, you move it over. By the way, same thing happens in the glass. In the glass over there, when the image we see doesn't come really straight through, like we're looking up or below, in the glass, to say this is our trees over here, that light ray coming from the tree kind of goes like that and goes, you know, normally you would think it would go straight through like that, but because of the refraction in the glass, it actually gets lowered a little bit. So when you look at this, you're not looking, in other words, if you were all of a sudden going to take a stick and shove it through the glass, you could just shove it through the glass where you see it. Would you hit that spot on the tree? No. By the way, how far is this moving? Like, you know, depending, the thicker the glass, the more it's going to move. But we're talking just, you know, like a millimeter, maybe, if that, a couple of millimeters off. But still, it moves a little bit. So keep in mind, the same things happen here as what's happening in our window. And if you've ever tried to spear fish and you look for the fish and you strike at the image of the fish, are you going to eat fish tonight? No. Because the fish ain't where you see it. Somewhere else. You actually have a concept builder about that. About spear fishing. Questions? Which leads us to Snell's law. Snell's law. And, okay, everybody look up here. I'll give you time to write it down, but I want your eyes. Everybody else. The product of the index of refraction of the incident medium, and that's a number that tells us about the speed of light in that medium. And the sine of the incident angle is equal to the index of refraction of the refraction medium and the sine of the refracted angle. Index of refraction n times the sine of the incident is equal to n2, which is that other index of refraction. Oops, excuse me. Sine of theta 2. Now, we're going to go more in depth of what n is in the next slide. So you guys copy down. But this is the law, Snell's law. So, the index of refraction. We use the symbol of a lowercase n. And n is that ratio of the speed of light, which is c. The speed of light in a vacuum is c. Our symbol is the c. So that's that speed of light in a vacuum to whatever the speed of light in the medium is. Keep in mind that's that transmission speed. Right? That's that rate of transmission going through. Value for c would be 3 times 10 to the 8th meters per second. And that's our speed of light. But a lot of times it's not expressed that way. It's not expressed that way. And because the minimum value, well, the best you can do would be if the index of refraction of vacuum, which would be c divided by c, which would be what? 1. N equals 1 is the lowest value. You can never have an index of refraction less than 1. So if you already got a problem, you end up in index refraction less than 1, you might have done something wrong. Because that's the lowest it can be. They're always going to be bigger. And the bigger the number, the slower the medium. The bigger, you might want to make a note of that. The bigger the index of refraction, the slower the medium. Okay? The lower the medium. Because 1 would be vacuum. That's the fastest. You get the diamond, which is almost like 2.5. Which is one of the slowest. But a lot of times, whether we do it by speed, you might get it this way. A medium might have be given to you as 0.8 c. It goes 0.8 the speed of light. Well, c divided by c is what? 1. And so this would be 1 over 0.8, and then you would deal it from there. So this is how sometimes they're given to you. They're not given to you in terms of meters per second, but they're given as how close to c, 0.8 c, 0.2 c, things like that. 0.2 of the speed of light. That sort of thing. Any questions? Well, we start working a couple of problems.
Yes.
Any more time? More time? All right, so let's write down this problem, and I'm going to do it for you, but we're going to go through this. This is a very typical problem. What is the refracted angle for a ray entering water, n equals 1.33, from air, n equals 1.003, if the incident angle is 35 degrees? Yes. Please write down the problem. What I like to do with these is to basically make a picture. So here's our boundary. So we have air and we have water. And N1, 1.0003, N2, 1.33. And there's our normal. Now, so we come in at theta 1 of 35 degrees. And now, since we're going from a lower to a higher index refraction, which means, what can we say about the speed? Are we going from a higher to lower speed or lower to higher speed?
Higher to lower.
Higher to lower. There, if we increase index refraction. So am I going to bend toward the normal or away from the normal? Toward. Toward the normal. So there's my theta 2, which I'm trying to find. But as a check, it should come out to be less than 35. If I get a normal greater than 35, I need to look at it. Snell's law. Now remember, those of you who are like in calculus and pre-calculus, stuff like that, for your calculators, you need them to be in degrees. Because you usually have your calculators in radians. So make sure these are done in degrees. One thing about water. I want to, while you guys are catching up, about water. This is really liquid water. This is the value for liquid water, though it varies a little bit depending on temperature and actually frequency. This is like an average value. Because depending on what the frequency of the light is and depending on what the temperature is, it does vary a little bit. So this is the average value. But for liquid water, someone I never thought about it, someone in one of the other classes asked, well, what about ice? Is it the same? I said, I have to think about that. And no, it isn't. The index refraction for ice is an average value of 1.31. Doesn't sound very far away, but there is a significance that light does travel a little faster in solid water. The transmission rate is a little faster in the solid than it is through the liquid. Glass. And if you look at different kinds of glass also vary in there. So glass is about 1.5. 1.5, but it does vary depending on what kind of glass you have on that. The average is around 1.5. So I do this. So I have sine of 35, which comes out to about 0.5357. Well, before I actually do that, I'm going to do a little algebra. Sine of theta 2 equals 1.003 times the sine of 35 degrees over 1.33. All right, everybody see my algebra there? Yeah. We're good with that? And when I do this math here, I get sine of 0.43139.
Are you missing a 0? 1.00?
3 zeros? Oh, over here. 0. Thank you. Now, if I ended up, what's the maximum value that a sine can equal? 1. Maximum a sine can be is 1. The minimum is 0. Sine has to be between 1 and 0. So if you don't end up between 1 and 0, there's a check. Okay? Now we need to take the arc sine. Now in your calculators, if you find the sine key, right above it is written above it usually sine to the minus first. That's the arc sine. That's how you get this number back into degrees or radians, depending on which we are. We're working degrees on that. So if I go, and usually that means you have to hit your second key, 0.43139. And I get theta 2 equal to 25.6 degrees. Did it come out less than 35? How did I do that?
Oh, no, I'm sure how she did that.
We did the arc sine. Above your sine key. You have a sine key on your scientific calculator. Above it, in most calculators, is the arc sine. That's one of those second functions. You have to hit your second key and hit that one. However, remember, different calculators deal with how you actually input the information differently. But that's the key you need to find an arc sine. Usually they're the same. Inverse sine, arc sine, same thing. The actual mathematic term is actually arc sine. Although a lot of people call it inverse sine because of this marking. I don't know why that might be a thing when calculator companies did that. But when you actually learn this, you used to write it out A-R-C-S-I-N-E, arc sine.
I didn't put the first answer right. So I put in what you put in, but it came up with
Is your calculator in radians?
I don't know. I never put it in radians.
Which one?
The second one. Now, that's okay.
This down here?
Yeah.
Did you put in 43139?
Yeah.
You might be in radians.
I don't know.
Or you may have done the cosine. I don't know what to say. Every class I've gotten this number, so I assume this is the right number. What? Again, it depends on your calculator. I don't know. Usually there's a function, some sort of function key that gets it out of degrees. All right, now you guys, everybody got this down? This is your sample. Now you guys are going to Can't do 55 here because you actually end up with a number, you actually end up having to do an arc sine of 1 point something. But it doesn't work.
Ready.
That's a whole different concept. Okay, so you guys, what is the refracted angle for an array entering crown glass, which has an n of 1.52, from the diamond? N equals 2.42 if the incident angle is 25 degrees. So you're going from glass, this crown glass, which is a type of glass, into the diamond, or from a diamond into the crown glass. So since we're going from a diamond into the crown glass, are we going to bend it toward or away from the normal? We're going from a larger to a smaller, we're going to bend away. So you should expect to see a number bigger than 25. All right, so I'll give you guys a few minutes to work on that. You may work together. This is not a quiz. You may work with your partner. Radians? It usually becomes something else. That's when you're dealing with trigonometric functions, the number one common mistake is if your calculator is in the wrong setting. Either you want radians, it's in degrees, or you're in degrees, or you want degrees, it's in radians. It's just that most mathematics is done in radians. Science is done in degrees. You know, it was nice in the old days, you know, when I was in high school, because calculators, basically you turned it off and went back to degrees. What? You should write down. This is more examples. When I was in college and high school, there was no such thing as a graphing calculator. Well, no, we actually learned why. We actually learned why they graph these. Hey, when I was in algebra, we didn't have calculators to do our trig. We had to do them by tables, by extrapolation. Made you appreciate it when I got a scientific calculator when I was like a junior in high school. It's when the price of calculators went down from like $200 to about $30. Basically, what you would pay about $10 for in a scientific calculator cost $30 or $40 when I was in high school. Which considered that was like in the late 70s, probably in today's dollars is more like about $100. Since gas was like, I think gas got really expensive when I was in high school. It was up to like about $1 a gallon. That was, when I was a kid, it was like 25 cents a gallon.
Oh. How do you get to do that for the price of oil?
Then the environmental movement started.
Do you not?
Right to do that.
What did you get?
Well, you know, Barack Obama said in his campaign he wouldn't mind $5 gasoline. He said that when he was campaigning.
Yeah.
Barack
How
Obama's
did
the
that
best.
work?
Barack's the best.
Hey, you know, history's going to say he's going to go down as one of the worst presidents. Jimmy Carter must love him because, you know, after this presidency, things have gone on. Whether it's his fault or not, things happened to Jimmy Carter that wasn't necessarily his fault. You know, he's going to replace Jimmy Carter as probably the worst president in modern history.
Yeah, right. George W. That guy had like. Yeah, that guy.
Let's see, inherited recession, it went away, he got bombed.
Who got
Basically
bombed?
because the Clinton administration wouldn't do anything about Osama bin Laden.
Barack Obama just caught Osama bin Laden. No one took permission to do anything.
Yeah, all the work there. Put it this way, you do know the Sudanese had actually arrested Osama bin Laden, and Bill Clinton's White House didn't want him. They said just set him free.
Yeah, right.
They were going to turn him over to us during the Clinton administration because he'd already bombed a couple of our embassies. I think Sudan or something like that had captured him, had him in custody, and was about to turn him over to the U.S. and the Clinton administration said let him go.
George W. Bush didn't want it.
Clinton was before Bush.
But then Bush came after.
Yeah, and
Exactly.
because the Clinton administration didn't do anything about terrorism.
But now we got it from Barack Obama.
I'm surprised he had the guts to let him do it.
We got it. We took out.
Like I said, he barely let the SEALs take out pirates a couple of years ago
So why didn't the Clintons do anything with that?
because they didn't consider it a problem. Because like all Democrats, they have no clue when it comes to foreign policy.
What's your take on
He's a pedophile.
Clinton's
a
I wouldn't
pedophile?
call him that. He was certainly a womanizer. I call him a misogynist.
A womanizer.
He's just a player.
42. Dude, no.
What a
I
beast.
don't think it says much for Hillary Clinton that she kept him around.
He's a manizer.
Exactly, that's why Bill said he's a beast.
There you go, Doctor.
Yes. Actually, after this, you can go.
I got the answer, Mr. Rizzo.
Okay, what'd you get for an final answer?
15.4.
It's got to be bigger than 25. Yeah. If we look at our thing here, here's our normal. We're going from the diamond. N equals 2.42 is our N1. Here's our theta 1 is 25 degrees. But because we're going to an N2 of 1.52, it's going to move away.
I put it in the wrong, like, yeah. So what you put is this,
It looks like an arrow.
So I have 2.42 times the sine of 25 equals 1.52 times the sine of theta 2. So the sine of theta 2 is going to be that 2.42 times the sine of 25 degrees over 1.52 after you do a little bit of algebra.
Yay!
Sine 25 is like 0.422 something
What?
times 2.42 divided by 1.52,
0.67.
and I get a sine of theta 2 of 0.672853 thereabouts. And so when I take the arc sine,
Mr. Rizzo, do you not round it?
well, I wouldn't round too much before you